Hello and welcome to the lecture CNN with Residual Connections, ResNet. So in this lecture we are going to discuss the relative analysis of deeper network and shallower network. Essentially we try to understand why deeper network may not always be good. Then we try to understand what are the reasons behind this. Firstly, we start with vanishing gradient problem. Then we try to understand other different problems like optimization issues, overfitting, etc. Then we introduce skip connection for residual network or ResNet and try to understand how skip connection is going to solve this problem and what are the basic advantages of skip connection and how skip connection make the ResNet very much popular and outperforms the other state-of-art model. Then we briefly discuss the ResNet architecture and finally we conclude the performance of the ResNet in the image recognition challenge. Today we will start another very important convolutional neural network. It's called ResNet. As per ImageNet large-scale visual recognition challenge, ResNet was proposed in 2015 and it outperforms the previous state of the arts. So two basic things what we can observe here, that number of layer is substantially higher, so it's a very deep network. And another very important thing, the error, top 5 error rate is become almost half from the previous SOTA. Now what we have to understand here, that ResNet allow so many layers and still it is outperforming the other, and that was the major problems what we understand in the previous lecture, that there is a certain problems of deeper network. So before beginning ResNet, let us recapitulate the problems of the deeper network from the shallower network. So what we understand about our deeper network, that's number of hidden layer between input and output is higher than the shallower network. But it is not always the case. The higher number of layer or a model with high number of hidden layer may not always perform good in comparison with the some shallower part or shallower network. Like here you can, this example you can see a 20 layer net, the error rate is low than a 56 layer. You can say one thing, that it is a test error. It may be the case of overfitting, because in general we know if model complexity is high, so it's a 56 layer more complex network, so definitely model complexity is very high, so definitely there is a chance of overfitting. So this is the maybe the case of overfitting. But very interestingly, in training case also we have observed that 56 layer net performing poor than a 20 layer net. It is not the case of overfitting. So there is some other optimization issues. In the previous lecture we have come across few of them, that means the covariate shift, vanishing gradient, etc. Let us just recapitulate these things and then we understand how ResNet is going to handle these issues. Now first to understand what is the major issue. Now you can say there is two. This network, left hand side network, is deeper than this right hand side network, that it is clearly visible. So one thing we can say, that whatever performance this Salver net, relatively Salver net, is performing, what accuracy is attaining, at least that accuracy it should attain, because up to this word set. So this part will be the identity mapping in that case, but still it is not been the case. So there is certain problems of higher number of layer. Maybe it is overfitting, maybe some optimization problem, maybe vanishing gradient problem, anything. So the thing what we conclude from here, the deeper net is not always better. That may be a vanishing gradient. Definitely vanishing gradient is a big issue. Then this harder credit assignment problems for deeper net, because these are more larger net. Some other optimization issues. Let's try to find out what are the problems. So what are the major challenges of these deeper networks? What we have understood, the vanishing gradient is one of the major issues, and these optimization issues like extra layers make training harder, the convergence become more complicated. Even this model, higher models or deeper models, fails to learn the identity mapping. So overfitting is another encode, internal covariate set. That we'll see one by one how ResNet is going to solve it. First, we are going to start with vanishing gradient. In our previous lecture, we have seen that in judicially selected or judicially choosing the activation function somewhat help to reduce the vanishing gradient problem. We have discussed that leaky ReLU is better choice than the sigmoidal or tanh nonlinearity. But still, leaky ReLU is not sufficient to reduce the vanishing gradient problem completely because of some reason. First of all, the small negative gradient is still there, because while leaky ReLU provides a non-zero gradient in this less than 0 case, so they are going to multiply the slope with very small numbers. That will definitely cause the vanishing or decaying the gradients. And in the case of deep network, this small value still cause this vanishing gradient issue. And another issue is saturation or dying ReLU problem. But we understand leaky ReLU is basically designed for fix the dying ReLU issue for the ReLU, and that's why it may not give the complete solution for this vanishing gradient, for mainly for the very high or very deep network. And since this ReLU avoids the hard zero derivative of the ReLU, this cumulative effect of multiplying many gradients leads still to vanishing. So what we have just said that time, to solve this vanishing gradient in very deep network are techniques like residual connection, and that is the main idea of ResNet, what we are start discussing today, are used, which allow vanishing gradient or which allow gradients to bypass the layers entirely. Let's try to understand what is this residual connection. Now ResNet basically use this residual connection. That's why it is called a residual network, or in short ResNet. So that what is the major thing? This shortcut connection, so also known as skip connections. Now this skip connection we have to understand. We are going to show you in diagrammatically what skip connection is. You can understand how this connection will help for vanishing gradient problem and other problems also. So what essentially it do? This skip connection allow gradients to bypass layers, solving the vanishing gradient problem. Definitely we are going to understand this. And it also enables training for much deeper networks that we have seen. 150 networks also it allow. So for this capability of ResNet, it is particularly suitable for computer vision tasks like image recognition or object detection, very complex vision task, very complex NLP task. By learning the residual mapping, that also you're going to understand what do you mean by residual mapping. And it is essentially the difference between input and desired output, and rather the detect transformation, but still we'll going to see. So these slides what we are basically try to introduce this skip connection or residual connection and how it helps. So in this particular lecture we are going to understand how this skip connection is going to solve vanishing gradient and other optimization problems and definitely the overfitting. Now let us try to understand what is this skip connections. Let's start with a very normal CNN layers. This is, so first we have to understand that this is AL, that means that it is input to a particular layer. Let's say it is Lth layer of a neural net or of a convolution neural network, and this is the L+1 layer. That we understand that it is layers of network. These layers of there's a hidden layers. They are hidden layers, and there is a different neuron. These are hypothetically very hypothetical example. What also we understand that when it is coming AL, it is multiplied with this weight matrix W of L+1 because AL is the input from the previous layer, multiplied with this matrix and add with the bias term of L+1 layer, that will make Z of L+1. And then we put our nonlinearity. It may be sigmoidal, it may be tanh, or most of the case we use ReLU or Leakey ReLU. So we get this. So that we understand from how we get AL+1 from AL. Similarly, we get this AL+2 from AL+1 like this. That AL+1 is input to this L+2 layer. So it is multiplied with weight matrix at this L+2 layer and then add this bias term, get the Z of L+2 and we get A of L+2 by imposing some nonlinearity on this Z. So this is a normal case, what we have discussed so far. Now what we are going to do in case of skip connection or residual connection, apart from this connection, we put this kind of skipping. Now this layer is being skipped with this. So here you can understand this L+1 layer is being skipped by this particular connection. That's why I got skip connection. Normal layer was as it is, and with addition there is a. So initially that was same, ZL+1 W L+1 A L plus B of L+1. That is very similar with this previous thing, and this is non-linear. But when we calculate Z of L+2, that is W L+2 L B plus L+2. Now when we calculate AL+2, then not only this Z of L+2 coming plus this AL is also coming. You see, initially it was only the nonlinearity is imposing over only Z. of L plus 2. Here it is not only Z of L plus 2, rather plus A of L. So this is the plane CNN, that what we have discussed earlier slide, and this is the residual connection, that this. Here it is only one connection we skip. Maybe we can skip two connection, maybe other three connection, maybe others. But this is essentially the concept of skip connection. It is very a trivial addition, but we can understand, we are going to see that its effect is very advantageous. Okay, so this is essentially a CNN with skips connection, or in say that this is a very naive structure of ResNet. So that is, I repeat here, here is the major changes, that this G, this activation function, for normal case it was on Z of L plus 2, here it is Z of L plus 2 plus this AL, and this AL is coming from here. Okay. Now we are going to understand what are the advantages of using the skip connection in residual network. Okay. So skip connection improves the gradient flow, that we'll see in the next part. Then it is optimization, allow identity mappings, speed up convergence, and enable very deep neural network without degradation. So first of all, what this residual connection helps, that is this somewhat handles the vanishing gradient problem. Then this identity mapping, that what we understood in the few slides back, that even if the copying by the higher layers is not done properly, this is called identity mapping. So this identity mapping things become easy for residual net. Then we'll see how optimization is being handled or become much better or easy. Then how it make the convergence faster. Feature reuse, it helps, and this regularization to handle overfitting. And definitely, since these problems are the problems of the deeper net, this skip connection solving this problem allow a very deep network, or you can say very robust. So what is important to understand, that is very important, that what is the solution, that this skip connection, the skip connection concept is very trivial, it is very easy to understand, but the small tricks solve so many problems. Vanishing gradient, identity mapping, better optimization, faster convergence, better feature use, reuse, regularization, and allow the deep network. Let's try to understand one by one. So we first start with vanishing gradient. Now before understand how it solves, let's recall that what is the vanishing gradient concept. In normal CNN, this error term is been calculated here. D is predicted output, this smaller d is target output, and difference of this is the error. We square it up, we use some normalization, and this is our squared error. Now this error is being computed at the output level, this is O. So what first we do, we compute the error gradient with respect to the WO, this parameter, output level parameter, that also we have discussed. Now in back propagation, what is happening, this error gradient is back propagating, so it is propagates from final layer to initial layer in a backward direction, that's why it's called back propagation. So now this particular error gradient, which is being detected or it is being determined at the output level, first what we'll going to get in the first, or it is the final hidden layer, just the hidden layer just before the output. This example, it is H3. This is only 3 header layer, one output layer. So how we can get this error gradient here? We are going to multiply this del of W0 by del of WH3. It is just a chain rule. We use chain rule to get the error gradient at this. And based on this error gradient, these weights are being updated. Based on this output level weight are updated. Based on this H3s are being updated. So here, next for H2, this thing again, this whole thing is again multiplied with del of WH3 by del of WH2 and so on. If we go more towards the initial layer H1, these things will be multiplied. So ultimately when we get initial layer, we get del of H2, del of H1 into del of WH3, del of WH2, del of WO by del of WH3, and into this the del of HO by del of WO, that is the output error gradient. Now if these values are very small, now this some value, this error gradient will keep on multiplied with a smaller value with less than 1. We have shown that most of the cases for sigmoidal lineage for these values is less than 1. And if it is multiplied with less than 1 values, then definitely this will be decaying. And now consider it is only 4. Now if there is a 40 layers, what will be happening of this? It will be very, very close to 0. Now if this error gradient is almost to 0 or very close to 0, then the weight parameter or weight updation is just not happening. Because in weight updation, what is happening? It was the W of t plus 1 equal to Wt minus this learning rate into this particular weight, or this is basically the gradient at that level. Now if this value is very close to 0, definitely there the weight parameters are not being changed or changed very low. So convergence become very, very low, or the convergence basically stop. So that caused the vanishing. Here we can, when these are small, these values are small, the gradient signal gets smaller and smaller and it back propagates to further from a final layer to the initial layer. So for very deep network, vanishing gradient become very complicated problem. I think we understand the vanishing gradient now. Now let's try to understand how this vanishing gradient problem is solved in case of ResNet. In case of ResNet, what is happening? Now you see what is Y, what is output, and this is fx, this value, this particular function is fx, and this fx, y is equal to what? Fx plus x. Okay, this is the x. So s is the identity that is for due to skip connection, or this x is input and fx is a few convolution error as it is shown here. Now if we calculate the gradient flow, observe the gradient flow with a skip connection, what is happening? What is gradient here? Del of L, del of x here. So this, what is y? You put del of del y of del of y, del of x. Okay. Now what happening? This del of L, del of y is there. Now we put this y value here, f of x plus x by dx. Now this del x, if we do this thing, it is basically d del of x by del x is 1. So it is essentially become del of L by del of y multiplied with del of x by del of x plus. what was the problem before? If this thing is very less, then gradient becomes low. But here there is a plus 1. So that is the main important to understand. In skip connection or this residual connection, put a plus 1 here and this make the change. So this plus 1 is very important. Even if this is very close to 0, gradient has a direct path. So even it is a 0, it is what? The del of L del of 1. This become this. So gradient does not vanish. And that we have to understand very properly. And that is why in this way this residual connection or skip connection helps to minimize or helps to solve this vanishing gradient problem. Now we are going to understand how skip connection help to implement the identity mapping. Now what do we mean by identity mapping? Given a base network, we want to put some extra layers here, and the idea is that if this extra layer is not contributing much, then this output should be reflected at the end of the network. But in ResNet, what we put some layer and we put this skip connection. You have to understand that how it helps this skip connection. Now here this ZL2 as our very popular equations, this weight matrix L plus 2 into L plus 1 is the previous input plus bias term, and this L plus 2 we put a nonlinearity over this and since this is skip connection, this AL is there. Now totally if we just put these values here, it is W of L plus 2, A of L plus 1 plus B of L plus 2 plus A. Now what we said, that these extra layers are not useful or is not contributing much. Then we can make these and these values as zeros. If we do this, these values and these values as zeros, then essentially what it come? This will be 0, so G of AL. Now exactly what we get here or here, it will come in here, and that is called identity mapping. So in this way, skip connection assure even extra layers is not contributing much, at least it map whatever the output of the base layer or the previous layer to the final output. And in this way, skip connection help to implement the identity mappings. Now next is, what is the optimization issue? Now optimization issue, it means basically that how faster it converge. Now here you have to understand, in case of plane layer, this is a input X and this is some convolution layers, some few convolution layers, and we get the Hx. In case of residual block, what is this is X, similar is this, but there is an extra feedback path, or this is extra basically residual path. So ultimately here we get Fx plus X as our Hx. Here it is Hx. So what is Fx? What we are basically learn? This is Fx. We are going to learn this Hx minus X. So the residual part, this X, is we are going to learn. So what we change is Fx. That is we going to learn. By learning what to change, that this Fx is easier than learning everything from that scratch. This Hx. That is definitely because this Fx is somewhat smaller than this complexity viewpoint or information viewpoint. So here this residual net is going to improvise or going to improve the kind of is optimization, or optimization is easier for this because that it basically learns the smaller thing. Exactly. So plane layer is basically this on the Hx, it is from very scratch, but this residual block is basically understand or basically implement this Fx with essentially Hx minus X. So this X is specific. So what is the residue part? Is yet to learning everything from scratch. What the change time is, Rex is change. So in this way, our this particular skip connection help to optimization procedure. Now there are several others advantage. So first of all, faster convergence. So where we understand the gradient flow is better because there is no vanishing gradient problem or something. So it assures the faster training because the gradient flow is better, and since the gradient flow is better, it not that much depends on the parameter initialization, and it is make the learning much stabler. So stable learning even early in training. Another important thing, the feature reuse. Earlier feature and edges texture are used in the deeper levels because of this skip connection. Because we can see here, please try to understand here that these connections, this connection is what? This connections is basically the initial primitive. So from here the initial layers is coming. So here it is not only this modalities or complex, it is the simple things that is also being copied. So it helps that kind of that feature reuse is very much. So earlier features, edges texture are used by the deeper layers. That is a very important aspect, and that is help for computer vision or NLP risk. So helps preserve low level spatial information. Here also, this is also we can try to understand low level spatial information here that even this low level spatial, the input is being copied here. Hypothetically I am saying. So here also these primitive patterns, more relatively primitive patterns are copied and so on. So we can say here that feature reusability is much, it will add lot of advantage and especially useful in vision task because that is there is a lot of context, lot of semantics concern. Next, regularization. This is for overfitting. The skip connection behave like ensemble of Salva networks because of this. So since ensembles of Salva networks, it generally increase the generalization, it improves the generalization, and definitely it reduces overfitting. So that is one advantage of the regularization. And robustness to the network depth. Now that is the cumulative effect. So due to skip connections, adding layers do not increase the chance of vanishing gradient, overfitting or optimization. That we have discussed in last slides. And since if these problems are not there, without any concern we can add on layers. So which makes the architecture more scalable, more modular. So and this skip connections requires no additional training parameters. So no extra complexity is being added. That is also a interesting. So what we understand here, that this skip connection is going to play a very vital role in visual network. So that it a lot of advantage over the normal convolution network. Now we are going to discuss the actual resonance architecture. It was proposed in 2015. So in this full ResNet architecture, this is somewhat look like this. Now one thing, we just make this particular any layer is bigger. Now here you can say to 3 by 3 convolution layer and such 128 convolution number of filters are there involved, and there is a skip connection like this. Okay, so stack residual blocks. Every residual block has 3 cross 3 layers and number of is 128. Okay, now after that you can see there is a periodically double the number of filters. It was previously 64, then 128, then 256 and 212, and downsample spatially the stride by 2 in each dimension. So the spatial resolution is maintained. Okay. Next, the additional convo layer at the very beginning. So we can put an additional convolution layer. This is the paper that has been given. Another interesting thing, there is no fully connected layer used. Only one FC layer of 1000 is used just for output classes, because there's a 1000 output class, because this image recognition challenge, and there is a global average pooling layer, is last convolution layer. So these are the important features of the paper, what the actual ResNet architecture being proposed. Okay. Now the different kind of depths, so it may be depths of 34, 50, 101, 152. This depends on here. Here it is the architecture, and if you put more additional layer as per the different depth. So these are the basic ResNet architecture. Now here what is the bottleneck thing. Now this bottleneck layer is basically explained here, that in bottleneck layer for deeper network we use the deeper bottleneck layer. What is the first convolution layer? It is a 256 channel bit. It changed the channel or reduced the channel to 64. So this 1 cross 1 make it from 256 to this is 64 actually. So it is the input connection. So it is 256. So it make it 64. So the 3 cross 3 does the heavy spatial processing, or not on the 256 rather than 64. And last one-to-one convolution is expand the channel back to the original. So these are the basic idea of this bottleneck layer. So for deeper network, ResNet use this bottleneck layer. Here also the similar thing. This is the input. First use the 64, make it channel 64. Then this 3 cross 3 convolution on the 64, and we get this output. And again put 1 cross 1 256, make it 256. So it will be ultimately the thing will be the same. Okay. Now this is the VGG 19 network, that this is as we understand clear, and this is 34 layer plane. There is a lot of problem that also we have, and this is 34 layer residual network, where this residual connection will be implemented to get the different advantage what we have. So here you can see the performance of the ResNet architecture, and you can see that this is plane 18 and plane 34. These are the basic 18 layers has a lower error than 34 layer, but here the case is different. This is 34 is lower than 18. So deeper the layer, better the performance here. So what thing we understand, that ResNet is going to solve the problem what the plane convolution layer faces when it is go to the very high number of hidden layer, or very in depth or very deeper architecture. So here you can see that ResNet is 34 is much better architecture or better result than the 18. So in summary, in this lecture we introduce first this ResNet. First we understand what is the basic difference between deep network and shallow network, and what is the problem of deeper network over making on the shallower network. Then we understand vanishing gradient problem, introduce Gibbs connection, that's a residual network or ResNet. Then we understand how or why skip connection are advantageous. Then we go through the ResNet architecture and we discuss some of the performance of the ResNet. The next module we start sequential modeling. We start with recurrent neural network. Thank you very much.